last speaker for this afternoon, Professor Makov, Haifa University, Department of Statistics of all places. He's also the head of the Actual Research Center, Actuarial Research Center, and he's also the head of Haifa University's Academic Faculty Union.
When Ellie suggested that I should give a talk here, I tried to find how I could fit in. And when I listened to some of the talks, I now know how I could fit in, because the impression I have is that if I told you that in some period in the future, maybe not long into the future, life expectancy will rise to 99 and age distribution will change dramatically, you will have to rewrite your papers, because age discrimination and pension system and all of it will be entirely different. So the need to project into the future and understand what life expectancy is going to look like next decade, 2 decades ahead, should have a major importance for us as researchers and for decision makers in society. Now, the paper I present here is a paper which is research in the Actuarial Research Center. Yasser Awad is a PhD student, and Bar-Lev and myself are 2 supervisors. And this kind of paper was sent to Eli, and he had a quick glance of it, and he said, I sent him a PowerPoint presentation with 50 slides, and he asked me whether I could remove the technical side of it. Well, I sent him another paper. This one contained only 3 slides. This introductory slide, the next one, outline of the talk, and the last one, thank you. Well, it was clear I had to replace some of the slides, which I did. But then as a precaution, I decided not to include the paper in the proceedings, just to make sure that you stay here. He also advised me that if the number drops below 5, I can stop. So I can now start because the number seems to be healthy. My talk will be a little bit about the art of modeling. And how do you take a model, how you modify a model, how you look into the science fiction of what next century will look like. I have great doubts about it, but I want to share it with you. So the talk outline will be, I'll give you some perspectives, and then some introduction on longevity and mortality modeling, just a glimpse of what modeling is all about. And then I'd like to talk about extension. I'd like to present some extension to what is called the Lee-Carter model, and we'll see what we can get out of it. By the way, 2 extensions are discussed here. One is how we actually make the mathematics of prediction, what we call the time series extension, and the other one, can we not focus on a single population, but can we look at several populations simultaneously and draw conclusions when we base our analysis on rather a broader framework, something which is not often done. Well, I looked at the longevity and mortality risk business, and I thought that where do I fit in? So I'll tell you where I don't fit in. Well, the first part here is about determining the nature of, if you like, risk exposure, like pension and the costs of nursing, etc. Well, this is not my domain. Now, the source of data and how you deal with it, I'll only touch upon it briefly. Forecasting the future is more what I'm going to talk about. And then, of course, when this is done, you can quantify risk, and you can then take decisions. And this is a whole spectrum of treatment of longevity risk, and I will really take my explain my very small role on stage number 3. First of all, when we talk about demographs and people who do actuarial work and mortality projections, some people look at the present, as you do. Some people look at the past, what I call archaeological actuaries, and some people look at the future, futuristic actuaries. And when you look at the past, some people spend their time actually to have a look at what was life expectancy in the past. And when you look at it, and it's quite incredible that until early 20th century, life expectancy was in many countries below 30. I'm not sure to what extent 67.2 is up to date, but it's around 70, I guess, these days. So we're talking about the whole span of human history with life expectancy was very, very short. On the other hand, when you look at the current, this is historical perspective. When we look at the present, and this picture shows the world I think in 2008. So you'll have countries like here where you have life expectancy below 40, and you have countries like here where life expectancy is over 80. So here is the global picture of life expectancy, and where is this picture heading to? Then I opened the UN projection document, and I looked at how they describe what will be the life expectancy in 2300. Even if they went as far as that, it's hard to believe. And they basically missed the big debate about looking at life expectancy in the future, because we have to talk about changes in patterns. Infant mortality that was dominant in the past has changed dramatically. And there are different patterns changing now. And then there are great discussion about biological limits. I mean, are we reaching our biological limits, or can we extend it beyond that? And then there are other things. How can you predict and make a focus about life expectancy when you have the periodic breakthroughs in science? They're talking about stem cells now as means of repairing body organs, etc. That would have tremendous impact on life expectancy. All these things are not included in models I'm going to discuss. So the big debate is held in one room, and the analysts are dealing with models in the other, and there is some lack of communication between them. Anyway, the UN came with future perspective for 2050 and 2300, and I was glad to see that. Sorry. Oh, that was very nice. Sorry. So you'll see that this is the top league. They're talking about Japan reaching 99 in 2300. You'll see that we're doing not too badly. Israel is here, reaching 96.7 then. And of course, at the end of the ladder, you have countries which are badly affected by AIDS, currently at 43 years, rising to 88 in the future. Sorry, this is in 250. They still need another 40 years before they reach 43.4, and then they reach 88. This is futuristic. How do they do that? Well, they do it by using models. And I'm using models too, but I'm very skeptical about it, and that's what I'd like to share with you. Now, the types of data we feed into our models is the following. We have the age effect, and what you see here is you see mortality rate taken in England in 2003, and checking how mortality is affected by age, and you can see that age contributes to mortality rate, as we all know. And of course, the rate and the curve and the shape will influence the impact of the data, but this is one source. Then we have the period effect of the year. When you look at people aged 50 20 years ago, or you look at people aged 50 these days, with take into account, for instance, cholesterol, treating medication, etc., the whole picture will change. So we see that over the years, mortality rate, this is for age 65, is declining. Will it decline any further? And when you take the two, age and year, they create what we call heat maps. Because, for instance, if I take, for instance, these years here, in the 70s, for young people, there were tremendous improvements in mortality at the time. But as we move to the 80s, amongst the young, there were hardly any improvements because they've already been looked after. So if you look at the warm colors, you see a diagonal here. So improvements took place in the 70s amongst the young, and they are increasing towards people aged 70 and 80 these days. This beautiful map was not created by myself, but I'll show you another way to look at the data when you have both age and time or period. and this is something which I generated using data from Australia and Belarus. I'll tell you why I choose the two later. But look at the Australian data. Well, if you look at it, this is the age, and this is the years from the 70s to the 90s, and you can see generally a steady increase in mortality as people are getting old, with little change over the years. This is Australia. But if you look at Belarus, the picture seems somewhat different, because you see, indeed, as people get older, they are suffering from increased mortality rate. But look at this shape here. There is a diagonal shape here, which I can only ascribe for the collapse of the USSR and the impact on life expectancy. I don't know whether you know, but in Russia, following the collapse, life expectancy of men went down below 60, which was tremendous change. So here, when you look, this is real data which I analyze. You just look at the data and you can see different shapes. How do you model these shapes? And then, of course, there is the cohort effect, which can be taken into account in the model. And there is the famous gold generation cohort. I'm sure many of you are aware of the finding that people who lived in England between the wars, 25 to 45, it was a very successful cohort in the sense that the life mortality, the mortality rate was reduced when they came to old age. Was it because they had less food to eat and they were forced to take diets of some kind? This is researched by other people, but there is the cohort effect. So the age and the year in the cohort are natural ingredient into any modeling of future life expectancy. And this is, for instance, a UK analysis of female mortality improvement. And you can see that these are the improvements, and these are the age groups. And you can see that as you move from 75 to 2000, you get better improvements in mortality rate. This is the peak at this point. In other words, it's not enough to know when the person was born, and what was his age now, and what was the year we were in, and etc., but also when he was born. So these are the natural ingredients into the model. Mortality is measured traditionally by taking the number of people who died to the number of people who lived at that age group at that year. X correspond to the age, and T for the year. This is what I'm using here in this presentation, which is what is called the central mortality rate. Other people, instead of talking about averages, just simply ask how many people die of a certain group. And the modeling is different. I don't want to go into that. But all my talk will concentrate how we can predict the central death rate, which is the number of people dead out of the number of people living at a certain age group at a certain year. And there are numerous models here, and I just put here a short list of famous models, and I'm concentrating on one, the first one, the Lee-Carter model, which was launched in '92, and still plays a dominant place in mortality projections. And there are others here, which I'm not going to cover, but I'd like to talk about what kind of ingredients you have into these models. So I'll show you a little bit of mathematical formulation. Okay. So here is the paper, the seminal paper of Lee and Carter in '92. And if you type in extension to Lee-Carter, and I'm contributing to that, you'll find many extensions to that. There is this kind of conservatism that if there is a model, a successful model, you cling to it and you try to modify it instead of maybe taking a completely fresh look and suggesting something entirely different. So I'm trying to modify this model in a direction which is quite fresh, and I'll explain later. But just to give you an idea, when you search the model on the left in Google, there are 114,000 entries. And now for a mathematical model of forecasting to have more than 100,000 entries in Google, it's quite a lot. But in Israel proper, if you do Lee-Carter mortality in Israel, you get 16,000. So I guess it is heavily used by the Israeli Bureau of Statistics, and maybe Bituach Leumi as well. I went to countries where maybe technology is not so advanced, and I took the intersection of Lee-Carter mortality and Yemen. And there were more than 2,000 entries. So it only shows that this is indeed a well-established model for projecting mortality. There are some parameters here which I'd like to mention. There are betas, there is K, and there is gamma. The beta corresponds to the age effect. And the K corresponds to the period. Are we in the 80s, 70s, 50s, or in the current millennium? And the gamma corresponds to the cohort effect. Well, I will only talk about the first two because the Lee-Carter model in its original form did not include the cohort effect. So my presentation will be limited to that. So what the Lee-Carter model says is that if you take the logarithm of the mortality rate, it has a linear function, which is a function of the age effect, of the period effect, and another parameter which relate the period to age, kind of an interaction effect. So first of all, I'd like you to notice that if we talk about a linear model, nothing could be simpler than a linear model. And this is a tendency of people, which is good, to try to model things in the simplest possible way. However, oversimplicity is sometimes a killer. And here we assumed some kind of linearity with respect to log mortality. If the model was modified, and some people did modify it, these authors, they added the cohort effect, which I'm not going to discuss. So here, this is the basis of the model, and the model itself looks like that. Now let me just show you what are the ingredients. You understand the difficulty. It assumes that the mortality, or the log mortality, at a certain age, at a certain time, is a linear function of age, the year, some kind of interactive parameter relating age and period, and some noise which is typically assumed to be normally distributed with constant variance. Now, don't be put off by statistical terms. There is a very strong assumption here. The variability of mortality is the same within every age. Would you support the view that mortality at the age of 50, variability of mortality at the age of 50 has the same as variability at the age of 70 or 90? This is, of course, absurd, but it's part of the model. Yeah, but I mean, if you look what the yeah, but what kind of probabilistic characteristic it had? It has a zero mean, and it has a constant variance. The variance is Avia. You are suggesting a wonderful extension to a model which does not incorporate that. There are something sigma is fixed across the ages.
Okay, I just talked about the notation.
No, notation is fine.
No, that depends on T.
And it,
What is T?
well, T is the year.
Never mind.
No. It's a constant variance. So this kind of a thing. And then you have this kind of thing which assumes that the impact of the year, time T, 2011, relates to 2010 plus a constant which is constant over the entire spectrum of ages and periods, etc. Plus again another noise which is a function of T, but it has a constant variance again. This is a very simplified model, but this is the dominant one that people use. Okay. Now let me talk about how you estimate these parameters very briefly. At the time when this model was introduced in 1992, there was a breakthrough in the statistical world because at that year, or maybe a couple of years before, a new methodology was introduced in the statistical world, which is called, the term itself is called Monte Carlo Markov chain simulations, which means that you can take complex models and simulate them in a certain way to get estimation of parameters which until then you were not able to get in a convenient way. I don't want to go into the technicalities itself, but basically this methodology suggests you fix some kind of prior distribution of the unknown parameters. You have some idea about what mortality rate is likely to be, and you fix your prior expectations about it, and then you use some mathematical models to generate the K, the impact of year, and eventually you do the simulation system which runs through the parameters. Now, our aim was to take the Lee-Carter model and modify it such that we can apply this new technology to estimate parameters. Not because we wanted to estimate the parameter of the Lee-Carter model, but because we wanted to use it in order to answer questions which the model itself failed to answer before. So what we did was to try and use this new methodology and see, for instance, whether we can change the model in one way or another. And we did make the first extension that we did was to try to estimate the trends of the model in different ways. And what we did was to take the Lee-Carter model and suggest 5 different models that could replace what we call the time series model. The first model one was the one that Lee-Carter himself used, and then we used other models that could be used instead. All of them, by the way, if I may go back on all of them, we're trying to replace this equation, which try to show the impact of period on the whole process of mortality projection. Now, what we did here was to test our tools in order to see whether we can eventually choose between the models, and I'll show you the final results here, because we took data, Irish and US data, from 59 to 99, and we have 24 age group for the US data, and we have 23 age group for the Irish data. And what we did is to run the data over a period of time and then try to predict the mortality rate of the remaining time. And this is the distribution of the mortality rates of in the US at the period we're talking about. And this was the Irish one. And you see the major difference here. I'll show the pictures. The history of Ireland and its demographic and court catastrophes in the 19th century and beyond created a very different picture altogether. And when we took the two and we tried to make predictions using the model, we got a prediction of the US data. You can see we're talking about until 2019, where mortality rate rose to nearly 0.5. And a similar picture came to Ireland, except they went up to 0.7. So we have more mortality rate in Ireland. But what model shall we use? I just show you I could make slight changes to the model. How can we check whether the model works well or not? Basically what we did, we cut the data in the year 1989 and make a prediction for the next 10 years, checking the accuracy of the models. And surprisingly, we found out that the first model, which was used by Lee-Carter and still being used by thousands of agencies predicting data, was not the superior model. The superior model was model number 2, which has a different mathematical structure than before, and I'm rating it as the most supreme model because it made better predictions in the 90s. So all of this was a kind of an experiment to see whether a new statistical methodology can be applied on the Lee-Carter model in order to suggest a new extension. And the new extension which we suggested, which is this one, was motivated by the following data. Let me just take a piece of paper, which I incidentally have in my pocket. And it gives population size of the oldest people, age 95 and beyond, in 1995. In 1995, in the US, there were more than 14,000 people living at the age of 100. And in the same year in Ireland, there were 53. Now, the ratio between 53 and 14,000 cannot be explained by the ratio of population size. If you go to 105, in the US in 1995 there were nearly 1,300 people, and in Ireland there were 1.9, which means one of the two died before the end of the year. And when we went to 110, there were 228 people in the US, but none in Ireland. Now, suppose I was trying to make a prediction of life expectancy in Ireland in the future, expecting, of course, that life expectancy will go up. I don't have Irish data. Irish data is non-existent for whatever historical, demographical, economic reasons. But can we expect that there is some kind of similarity between Ireland and other countries where this data exists? Can we borrow data from one country to another? Well, this is a question that needs to be answered. Now, of course, I wouldn't take US data and mix it with data from Uganda because of the major differences. But for instance, suppose I took the data in Scandinavia, where you have countries that share the same kind of technology and know-how and hygiene and level of medicine, etc. Why can't I take the very few cases of people living beyond 100 and 105, 110 in order to accumulate the data, in order to learn about patterns of mortality into the very old age, in order to create the models for prediction? Now the point is, how do you do that? By gathering the data on the one hand, but preserving the identity of individual countries at the same time. So how do you keep the Finnish data intact by borrowing data from Finland to Denmark and vice versa, etc. So this is basically what we aim to do, and what we did before was a little experiment that showed that we have the tools to do it. When you do this kind of what I call the new statistical methodology, basically the number of people who died are affected by a certain death rate, which is affected by age and by year and by another parameter that relate age and year. But these parameters are also fed by other parameters, which are the distribution of this parameter, which are unknown. So there is a whole sequence of parameters leading the model in a hierarchical way until you get to D, which is what you try to predict. Now, you'll have a map like that for Ireland, and you'll have a map for that for the USA. Or maybe you'll have a map for that for the European Union. Take, for instance, beta, which is the one relating age to time. Would I say that when I take the beta of every one country in a community, they are related? Is it possible that basically are drawn from a superior distribution where every member of that population, be a member of the European Union, member of the Scandinavian countries, share some similarity? And this is what we suggested, to take in this flowchart, to take, for instance, beta, and instead of having a single beta for a single country, assume there is a superior distribution of mechanism relating to that part of the world, with the characteristic of that part, with the technology, medicine, hygiene, and everything, and say, okay, these countries share the same kind of phenomena. They come from a similar distribution. We generated a distribution of betas coming from a superior beta. The same we will do to the alpha, the same we'll do to every other parameter. Okay, we did that. And the results are quite interesting. Let me show you what happens when you take alpha, the impact of age. Take for instance the US, and you take Ireland. The red distribution is the distribution that generates the individual country's age effect. So if there was another country in the pool, and I'm not saying Ireland is similar to the US, but for convenience I took the two countries. If I drew more countries, the alpha would come from the red distribution. So maybe if I took another country, it would be around here or around here, but it's unlikely to be here, it's unlikely to be here. Now what you see here, this is the possible values of the age effect of the US. And this is the possible value of the US, of the alpha effect, the age effect of Ireland. But you can see there are two distributions here. There's one broken line, one solid. One broken line, one solid. This is what happens when you take the US you take separately, you get the pink broken line, and when you take the US together with Ireland, you get a shift and you get the green one. Similarly, if I take the beta, you can see that the betas come from a superior distribution. With the US, there's hardly any difference whether you apply the method or not. With Ireland, suffering from lack of data, the blue, which is the distribution of the age effect following introduction of the US data into the pool, changes the picture from the pink to the blue. So these are nice pictures. What kind of impact does it have? Well, I'll show you a picture of. Let me skip to validation. we took the mortality age of 105. As estimated in the US, and US with this combined method and without. In Ireland, with and without, this is without and this is with combining the data with the US. What you see here is the error rate. We actually measure how inaccurate we are. With the US, where you have a vast amount of data, the changes when you use our combined method is minimal. But when you go to Ireland, and you can see that the Irish data, before you introduce the US data into the pool, engage in a rather higher error. When you introduce the data here, you get a smaller error. So in other words, the method proves empirically that when you combine data from various countries, you can pull in the data and make better prediction of age of mortality at ages older than 100 and beyond. So this is an experiment in modeling which try to take a model which I not entirely agree with and need to be corrected and has been corrected by others, but try to introduce something which is simultaneous projections into our global village by pulling data from various sources. Thank you.
I'm not following the technique, of course, but I have a kind of methodological question. You have the data for Ireland. For what happened? Okay, so you have the real data. What happened? So many people survived, so many people died. You have the real data. Now, you tell us that you combine this with data from the US and other countries, and you have a better prediction. But better prediction of what? Since you have the, how can you know that this kind of synthetic prediction is better than what you have from Ireland? Well, what you have is only the data from Ireland. How can you improve? Or
the proof of the pudding is in testing it. What we did was we took the data from 89 to 99. Irish data, Irish mortality rate in the age of 105. Okay? And what we did was to predict how many people would survive at the age of 105 in 89, 90, 91, and all the way to 99. And we did it in 2 runs. The first one, we took the model where I use only Irish data, using the Irish data only to build the model until 89, and check its prediction over a decade where we have the actual data and measure the discrepancy. Then we take the combined data of the US and Ireland, which allows individual reflection and joint reflections into the model. We stopped at 89 and we used the same model to predict what will happen 10 years on. In the US, there was little effect. But in Ireland, there was a major
okay. So in fact, you just had more observations. If it's from the same population, you have more observation, and then you have a better sample, then you can have a better prediction.
That's a principle.
It's as simple as that, isn't it?
Yeah, it's simple as that. What is difficult, how you combine the data. Of course, the moral is, yes, you have more data, you have better, but how you have more than one way to combine data from different sources. Yeah.
Two questions. The first one, this better prediction works with whatever countries you add to the analysis, or it's robust? I mean, it's in econometric terms, or it's just a hazard, or, I mean, you can replicate your result 10,000 times and you get the same thing? That's the first question. The second question is about uncertainty in life expectancy estimation. This is really a huge issue because, as you certainly know, pension systems are linking more and more pensionable age to increase longevity. So we have shown in one chapter of Pension at a Glance of this year that using the UN mortality scenarios and taking the low mortality and the high mortality and the median mortality, if we have a distribution of mortality, this would imply, for example, that for some countries there will be a difference of 2 or 3 years in the pensionable age. That this is huge in terms of finances. So, and this means that the projections in terms of mortality have huge consequences in terms of the finance of public finance, where this is related to where pension systems are financed on the basis of public budget. So I was wondering if you know, I mean, the chart we have, but it's quite amazing, and this is the UK projections in mortality from 80, I think it's, the first one is 81, and the last one we had here, because after, is 2004, and there has been a kind of huge change, I think 7 or 8 years during the same period. So how to avoid this kind of mistakes in, or...
Let me start with the first question. This is at a very experimental stage. I would not advocate taking any countries at random and pulling in the data. But the point is that I was giving this paper based on that in Australia, and I thought what would be interesting for Australia is to compare mortality projection in Australia compared to neighboring countries like Malaysia, Indonesia, etc. You can't get any data. So when I was in Australia, I showed that. Of course, what Belarus has to do with Australia? So it was only like an exercise. And again, the data with Ireland and the US, which shows it because of the ease in obtaining the data. But I think that more seriously, I would take countries where the inherent variability is the same, like in Scandinavia, in Western Europe, etc., etc. As to avoiding the mistakes you see in the UK predictions, well, the mistakes are based on automatic usage of models. If you use a model and you believe in it without taking into it parts of the debate I talked before, etc., then you're likely to be surprised. So basically, the conclusion is that you have to build models, but you have to assess the quality of the models and make some input into the models, which based on new technology and other things which are happening at one point or another.
But my point is there any way to reduce the uncertainty of life expectancy in modeling in the future, or because you were presenting the data from the UN and you really seemed very skeptical about, I am too, about the 2300 projections.
I think they're underestimating it.
Yes, they are,
yeah.
probably. But so what we can do? I mean,
develop better models.
I think you answered part of my question, if I understood correctly what was presented, but the basis for pooling data across countries is based on two things, if I understood correctly. First of all, the availability of data. If there's no data, you can't pool them. But number two, some kind of theoretical affinity between the two populations. How much affinity is required? How do we know when enough is enough? And what is the basis for the decision?
Well, I have no answer for that. I pointed out this is an important issue. And I think we can try and look at it experimentally by taking countries with what is obvious close affinity and countries with gradually diminishing affinity and see what kind of impact it has on the quality of predictions. But this hasn't been done.
All right, thank you so much.
Thank you.
Udi. We're going to a restaurant now. I think of the mortality rates. I guess we ought to order hopeful food. It's a health food. So we'll have cabs waiting downstairs.